Hello students. Welcome to the class 5 of this online outgoing course for this January 2022 CSIR NET. So I have uploaded the 4 classes already. So if you haven't watched it, so please watch. That is my first request to you. If you don't watch, then you won't be able to get maximum benefit to it. Today, after finishing that center source discussion in the last class, today we'll be discussing Lagrangian and Hamiltonian formulation, some basic things. Then we'll move into the next class, we'll move into some other details like page space, plots, and then to canonical transformations and etc. So first, the first question which should come to your mind, that what is that Lagrangian formulation and what is the necessity of doing this once you already have the Newtonian formulation? Does the Lagrangian formulation means a new theory of mechanics? No. Actually, Newton's equation of motion already predicted the motion of any object. So in principle, if you know the force, then you can integrate it and get position as a function of time, and that was the motto, the goal of the mechanics. But we have many problems in doing the Newtonian formulation. That is why this Lagrangian came, and it had philosophical implications also. We will discuss both. So first, there will be technical problems we'll discuss. In the Newtonian formulation, we start with force. But many times the force may not be known. The force may not be known, and if it is known, then also there comes many constraint forces like tension, the T, the reaction forces, that N or R, whatever you like it. These forces comes, and these are not easy to handle always. So this will be a little bit tough to handle. That is one problem. Then the next problem will be the forces may depend on time, location, even velocity. Then things will get a little bit complicated. And there will always be 3 coordinates for a point object and 3 n coordinates for the n particles. So to summarize, what are the problems we basically feel in Newtonian mechanics? First is force might not be known, and the reaction forces like tensions, the constraint forces like tension and the reaction forces comes, and they may not be known and may not be we may not be able to evaluate this also. There will be a problem. Evaluating the forces and the integration might be a difficult task, so that is okay. More important problem is the number of coordinates is always very high, 3 for a point object, 3n for n particles. So all the problems will get a little bit easier. Handling of this problem will be a little bit easier in Lagrangian formulation. I don't say that nothing will be there. There will be some problem, but these problems might not be present in the Lagrangian mechanics. So before we do this, I will have a slide. So I don't have it retyped. So in Lagrangian formulation, we start with energy. So knowledge of force is not required. It's not required. That is one thing. So no tension, reaction, etc. needs to be known or needs to be calculated. That is one problem. Second is generalized coordinate. We use generalized coordinate there. The minimum number of, you please do a read from a good book. I will tell the minimum number of required coordinate to completely describe a problem. Okay, so in Lagrangian formulation these are there. Next, from where the basic should be read. So please read Landau volume 1. That is the best book to have a good knowledge on classical mechanics, Lagrangian and Hamiltonian formulation, and all the basic laws of mechanics. Landau Theoretical Physics volume 1. The title is Mechanics. The Physics volume 1. The title is Mechanics. Please have a read. Please, please, please. If you are doing physics, if you will be doing PhDs, then of course, please read it. Okay. Next. From our prior knowledge, we know that L is T minus B. Does L mean T minus B always? This is a basic question. Read Goldstein also, but Goldstein will be a little bit tough. Landau is also a little bit tough, but okay, Goldstein is more detailed, so Goldstein is a must book. You don't have much time now, so please have a read on Landau, few pages at least. So okay, let's go. If does L means T minus B always? No. L is T minus V only when there is no velocity dependent potential. There is no velocity dependent potential, then L is T minus B, otherwise L is not T minus B. Otherwise L is not T minus B. Remember that. If velocity is only a function of position and time, then L is T minus V. Okay, what are the other assumptions which we take in Lagrangian formulation? We take few assumptions. One is the constraints are holonomic. What is a holonomic constraint? Please revise the constraint parts from any book, Goldstein or the Spiegel theoretical mechanics will also work. Constant forces do not work. Constant force do not work means there is no work done by the constant forces. The forces are conservative. Non-conservative force, our Lagrangian equation does not work. Of course, we have a way to apply Lagrangian formulation on non-conservative forces also. That example, that Theorem example is properly done in Goldstein, so you can do it. But for the simple formulations, we do only conservative forces. The potential V does not depend on velocity. So potential should not be velocity dependent. Potential should not be velocity dependent. Then we will apply L equals to T minus B, and this is Lagrange's equation. This is Lagrange's equation, as you know. And from this Lagrange's equation, we have a very immediate consequences. We define this Pj as del L del Qj. This is as generalized momentum. It might be a linear momentum. This might be a angular momentum. This might be both. And the first consequences is if L is independent of Q, if L does not depend on a particular coordinate. Okay, this J is a sum over all the coordinates. J index signifies that for each of your coordinate you will get one separate Lagrange's equation. So if your L is independent of Q, then del L del Qj is 0, and that means ddt of del L del Qj dot is 0. That means del L del Qj dot is constant. One dot is missing here, means may not be visible. So okay, so your Pj is del L del Qj dot will be a constant. This is a very important. This have very important consequences in throughout the mechanics. So remember it very well. So if your L is independent of a particular coordinate, generalized momentum corresponding to that particular coordinate should be a constant. So I think you are seeing my head there. So may I will just write again to have a to show its importance. Del L del Q J dot ddt minus del L del Q J, that is the Lagrange's equation. If del L del Qj is 0 for any coordinate, then ddt of del L del Qj is 0, hence del L del Qj is constant. That is very important. We'll discuss the philosophical aspect of this. Now what we have in our next slide, we will have more importance, another important aspect of Lagrangian, which is the non-uniqueness of Lagrangian. What is non-uniqueness of Lagrangian? For a particular system, Lagrangian is not unique. Means many different Lagrangian may describe a same system. Means if you have one system, say you are just running, so your state of run might be represented by 3-4 different Lagrangians. So Lagrangian is not unique for a given system. If a Lagrangian L describe a system, if a Lagrangian L describe a system, then L dash, if we add with L a function of a total derivative of a function of space time, then your system remains the same. That means if a Lagrangian L describe a system and you add ddt of f, what is f? F is an analytic function of space and time. F is a function of p, q and t. So f is an analytic function of position and time. So if you add, f could be any function. So this is a generalized transformation, could be called a gauge transformation. So if you add df dt, f is any function of space and time with a Lagrangian, the resultant Lagrangian will describe the system equally well. So this would be a Lagrangian for the system also. Both L and L dash will describe the same system if L dash and L differ by a position of derivative of position of space and time. Sorry, derivative of a function of space and time. So that I told. So that means if we had total time derivative of any function of generalized coordinate time with a Lagrangian, the equation of motion remains unchanged. So you can prove it, you can verify it. Each and every book have that theory. So we using the df dt is we write a total derivative like this: df as del f del q q dq plus del f del t delta t. So then df dt will be just like a two variable function what we do in very mathematical physics. So if you don't have any idea about what it is, how it's coming and why we should write it, then you please read the basic two variable calculus from any basic book like iblbifl. So this df is delta f delta q plus delta f delta t delta t, then df dt is this, and you use this and you prove this. So this is a home task. So this will be a 1-2 liner, but please do this. Using this, please prove that both this L and L dash will have a similar that Lagrangian equation of motion, they will follow. So okay, then next we have, okay, then we have example 1-2 examples for the conservation. Now I will little bit discuss more about the philosophical aspect. So Lagrangian have a philosophical aspect also. So as we have shown that if del L del Q J, you may write for a particular coordinate J, so then Pj is constant. That means for a, if L is invariant of some transformation, then the generator of that transformation, what will be the generator? When we will discuss the canonical transformation, we will discuss it more detail. But as we will see, if we see del L del theta is 0, we can prove it that your main L is constant, Z is constant, that is angular momentum. And when you see that del dt is 0, so no, sorry, not del dt, so there we are. It's generally then Hamiltonian will be energy will be constant, which means these three are related, x with px, theta with angular momentum. So this is Lz because we define x, y and theta like this. So the angular momentum which is perpendicular to that plane in which the theta is defined. Then say time with energy. This is energy. This is angular momentum. This is linear momentum. So these are related. If Lagrangian is independent of this, L or H, the Hamiltonian is independent of this, then they are conserved. So from here also actually the space-time symmetry and conservation theorem comes, that if anything is conserved, there is any symmetry in a space-time, so there is some quantity associated with this which will be conserved, which will be preserved. So these are conjugate sets. So translation is somehow related with linear momentum, the rotation is somehow related with angular momentum, and the time is somehow related with energy. And the invariance can be inferred philosophically as, if your Lagrangian is independent of x, or if your Lagrangian is independent of theta, and if your Lagrangian is independent of time, that can be inferred like this: if some system of law, or if the laws of some systems are homogeneous, isotropic and time independent, then the linear momentum, angular momentum and energy are conserved. So there you can think like this, and many philosophers think like this, that in general in nature we have this linear momentum, angular momentum and energy conservation formulas. So the origin of this conservation formulas are somehow related with the symmetry of the universe. The laws of nature, which are the laws of physics, are homogeneous, isotropic and time independent, which means the laws of physics are same in India, same in say Vizag, same in India, same in America, same in Australia. Like any displacement, any translation you go, anywhere you go, laws are same. Any direction you go, laws are same. And laws are same in time. Say 1000 years ago, the laws were same. 1,000,000 years after this, the laws will be same. So that is the basic philosophy of this symmetry and conservation. If you do physics, if you do theoretical physics, this will come again and again, again and again. These are very important. I hope you understood what I tell. If you didn't, then please have a revise. Please go back one few minutes, then you start learn this, listen once again. There is no mathematics in it right now, but just listen it. Okay, so there are many problems which we can handle with Lagrangian. There are many in the problem set. There are many problems, so please do problems from the problem set. We'll do one two very important problems, very tricky problem which you might got erroneously, that you might get it wrong. These problems one two you may discuss. Say what to tell. Say if you have a Lagrangian like this, you have a change the font G-Fred bold. Okay, so this is a don't you have, no, we could save some space. This should have been labeled, it's grouped together. Okay, so we have spaces. So you are given a Lagrangian. So you are given a Lagrangian, that is given. I should change this. This is given a Lagrangian. This is the potential. They are asked, yeah, Lagrangian is independent of time, their energy is conserved. So you are asked how many conserved coordinate will be there. You are asked how many generalized momentum will be conserved. So just after looking this problem, you might say Lagrangian is dependent on x, y, z, all three. So there is no coordinate like which we take del L del x equals to 0 or del L del y equals to 0 or del L del z equals to 0. We cannot tell. So there is no angular momentum is conserved. You may conclude, but that will be wrong. You may say, okay sir, we are saying these are non-zero, del L del x not equals to 0, del L del y not equals to 0. They are all not equals to 0. So then there is no conserved angular momentum or no conserved linear momentum, but that will be wrong. Sometimes we miss the hidden symmetry of the problem. So looking at the potential, you look both things. You just look in which the potential is dependent on. The potential is dependent on which coordinates, and whether potential is dependent on velocity or not. But also don't miss the symmetry. What is the symmetry? See, we can write this from Cartesian, we can write it to cylindrical, or from that Cartesian we write into a spherical polar. So if you write this in cylindrical or polar, then things looks little bit different. So this is the same Lagrangian in cylindrical coordinate system, and the same Lagrangian coordinate, and the same Lagrangian is written as in spherical polar. Can I increase the space among this? No, it is increased. And this is for spherical coordinate. So if you transform the Lagrangian into from Cartesian to cylindrical and from Cartesian to spherical, you see that the potential is now, it's x square plus y square plus z square is now rho square plus z square. So you see that phi del L del phi is conserved. You see here also, you see that del L del phi is conserved. So potential is has become x square plus y square from z square to r square only. So there is del L del r, there will be a del L del theta, but there will not be and del L del phi. So yeah, so I think I delete all this. So these are not that required. So what I wanted to say that if you look at a potential, then look at its symmetry also. Then you conclude that your how much, how many uh, generalized, how many conserved quantity will be there. So energy will be conserved, and there is angular momentum is to be conserved. So you need to perform a coordinate transformation. So we may have a, I should not go too much with this. So there are many topics to be covered. So then what I will leave this to you. So always look at the symmetry of the problem. So without the symmetry nothing is there. So always look at the symmetry. Another thing I wanted to discuss is, does all the Lagrangian have a physical proper Hamiltonian? And what is Hamiltonian? Hamiltonian is by definition, you know, it's the sum over the momentums with multiplied by the velocities. Then you took a sum, then subtract your L. Does all Lagrangian have a proper Hamiltonian? Does it? It might not have. Okay, let's see. This is a given that you are asked that Lagrangian of a system by a single generalized coordinate q is L equals to half of q dot sine square q. Its Hamiltonian is, what will be its Hamiltonian? Then you might calculate, from this Lagrangian half of q dot sine square q, you calculate. P is del L del q dot, so that will be sine square q by 2. PQ dot will be q dot sine square q by 2. Then your Hamiltonian will be 0. Hamiltonian may not be 0. Energy of a system may be, of course, 0, positive, 1, negative, whatever. But you don't get an analytic Hamiltonian here. So Hamiltonian is 0. So now the question, it can be the Hamiltonian of physical system can maybe 0. No, physical system may not be 0. So that Lagrangian, that Hamiltonian of this problem should be undefined. It is not 0, whether it is not defined. So we may explore a little bit. It is not 0. So let's calculate the Lagrange's equation of motion of that given Lagrangian. From this Lagrangian, if you want to calculate the Lagrange's equation of motion from this, what you will get? Del L del q dot is this, you already know del L del q is this. So if you calculate ddt of del L del q dot, then that will be q dot sine q cos q, and del L del q is also q dot sine q cos q. So did all this to become 0. So you did not, you calculate yourself once, so you did not get a valid Lagrange's equation of motion of the particle. So the Lagrange's equation of motion itself does not exist for that particle. So that system does not exist. The system is totally imaginary. That system cannot exist. So this is a Lagrangian. You can write a Lagrangian. You can write any function of space q and q dot, all these things. But that does not necessarily means that does not necessarily represent an analytical system, a proper system. So you can write any function. You can write any function of q and q dot. So if you ask me, said, does this system represent an Lagrangian? If you are give me any function, so I will check that. Okay, I will tell you that. Okay, let's calculate its Lagrange's equation of motion. Let's calculate its Hamiltonian. If we get a proper analytical equation of motion, a feasible equation of motion, and a proper looking, good looking Hamiltonian, good looking equation of motion, then of course we can. But if you calculating Hamiltonian, you get 0, you do not get a Lagrange's equation of motion, then that means that this is not defined. So this is a one important knowledge which many books misses. I haven't seen this discussed in any book. This is a question asked in TIFR. So this is a question asked in TIFR. TIFR people are very smart, so they asked for this. So we perform this thing. Okay, then we discussed a little bit of theory of Lagrangian and some interesting aspect. So okay, now just a review on what Hamiltonian is. You know Hamiltonian is Pj Qj dot minus L. Qj and Pj have a relation. This is called Hamilton's canonical equation of motion. You are when this both left side has derivative Qj dot is del H del Pj. You remember that when you are writing Q, you are derivating with respect to P, and when you are writing P, you are derivating with respect to Q. And when P comes, there is a minus come. This is Newton's second law, that force is equal to dp dt. Minus comes because of the relation between force and potential. There is a minus. So that is the basic part. Next class we will discuss the phase transformation, sorry, phase space calculation things. So we need to draw the phase space diagrams for many mechanics problems. So we'll discuss that. But before we do, we just have a look on that Lagrangian problems. So these Lagrangian problems, this first problem, you may think that answer key is wrong, but answer key is okay, because there is a potential energy part which you should not mistake. But why this particle is accelerating? You should have a potential energy term. So answer key is perfectly fine. This is also a generalized coordinate and constant problems. These are basic. This is a virial theorem problem. So remember what virial theorem statement we did in the central force class. So don't forget it. These are very elementary problem. These are just solve this Lagrange's equation. Just solve the Lagrange. So these are also fine. These are also very easy problems. So all these problems are very easy. I tried to make this problem sorted like from in the ascending order of difficulties. So first few problems will get easier, easier, slight difficult, easy. This is the standard theory of double pendulum. So all these problems were asked in the previous question. This is a very standard problem, slight difficult. Coordinate transformation you need to use. This is you need to solve after calculating the equation of motion. This is the problem we discussed, that there is a symmetry x square plus y square. There is no symmetry in z square, so that two x square and y square together they will form the rho square, so that phi will not be there. So that angular momentum along Lz should be the constant. So think on this Lz. Okay. So equation of motion of a system is described by, okay, just this time dependent Lagrangian is a very preferable or very liked by the paper setter. So these are repeated, so just solve it. Lagrangian of a particular, okay, given a Lagrangian you need to calculate the canonical momentum. Okay, so oh, just remember one thing. All right, always write h in terms of, many of you do the mistake, each you write not in terms of velocity but not, and not in terms of velocity. It's just like h is like, say, e square by 2m plus b as a function of q. Write like this. You write like this, but don't write in terms of velocity. So, okay, this is to be calculated. These are not a Lagrangian problem. This is a just this came here, but this is dimension analysis problem, so I just don't know how it came, but it came here, so just keep it here. The sqword is nothing, this is just a space command typing mistake. So from here also, this is a little bit a difficult problem, so you need to transform the coordinates in a proper way. So if you can do it, you will be able to do. So we'll keep this discussion left until we discuss the small oscillation part. We have very small time, but coordinate transformation is very important, so you need to do this always many times. Potential energy is given, then what will be the constant of motion? This is just solving, this is just transforming the Lagrangian into some other coordinate system. Each and every problem is fine, you just calculate this, so all the problems that are uploaded in the Google Classroom. So this is also a kind of real theorem type of problem, generalized potential type of problem. So see how this problem has been done, but this can be done by the averages. This is not a very tough question, but the same funda in statistical mechanics we use when we use the generalized equipartition theorem. The same funda we will use also. Those people who know, they are understanding my words. Those who does not know anything, so I cannot do for you people, please, I'm sorry. I just do this course in very less time. So this is just a motivation type of course. You know something, you just get motivated. If you are starting from the very basic, just you are starting from total zero, then you need to prepare for at least 1 year to get this much level, to achieve that much level. So if you are starting with a very basic thing, so then you start with very basics. Still this can be a guide that what you need to do, but you might not be able to understand half of my words, so don't worry. These are theory, conservation principle. This is also a theory type of argument is there. So we just discussed all these things. So please let me know if you are not able to get out. Please discuss in the Facebook group that if you are getting a mistake. This is also a Lagrangian calculation problem. For the free particle, what could be a possible Lagrangian? So you just need to see that which Lagrangian leads to a free particle. So this is, here you need to solve the Lagrangian. Here you need to calculate. No, you don't need to calculate the Lagrangian. It's just to think about the constraints. So you think about the constant. This is little bit difficult. I calculated it. This will be little bit difficult. Okay. This is also a little bit difficult problem, but you might have a try. This will also be a difficult problem, but you might have a try. After you finish, thing is, if you did till question 35, then you attempt 36. You directly attempt 36, then you are not going to get anything from out of it. So just do one by one. Don't skip it. Do 36, then do 37, then do 38, one by one. This question is technically wrong, but yeah, I understood what the paper setters wanted to understand, make it, but this is technically wrong. So okay, I have tried. I given the answer keys, some solutions, some. Okay, Sandeep worked the solutions beautifully. Both together we did. Sandeep did the solution part. Sandeep contribution is more than me. So okay, okay, so that's much of our Lagrangian Hamiltonian basic discussion. Next class I will have, next class we will do phase space plot, very important. Next class, phase space plot, that will be very important. Space diagram or phase diagram plot, that will be very important, so don't miss it out. Next class, tomorrow I will upload it. This is Friday. Saturday definitely I will upload. So if you thank you very much for this. Don't phone me, do a WhatsApp on this, email, Facebook page, Facebook group, YouTube, all links are there. You just can type and go, just, or you can search. If you have not joined this course yet, then please join with this Google Classroom code iblbifl. All the notes, slides I upload there, all the problem sets, all my own notes for mechanics is uploaded there. And after finishing the mechanics, we'll move into electrodynamics also. So please join this Google Classroom to get most benefit of it. If you are getting that this class is full or some error, then there should be a second code written in the description of the file, sorry, of the video. So you'll get it anyways. So thank you so much to attending the lecture. I don't know how many of you are still with me, but yeah, if you are, then I'm delighted. Okay, thank you.